Hi guys, welcome back to 100 Days Machine Learning Crash Course. Today we want to talk about batch normalization and also convolutional layers and max pooling. Okay, first we want to talk about batch normalization. Recall what was the normalizing, and in normalizing, when we had the training dataset, for each feature we calculated the mean and the variance, and then we removed the mean from each of the input and normalized the scale of the input. Okay, we called it input normalization. Okay, now if you remember that in weight initialization, we have seen that we are glad that the distribution of the output of the neurons are something like Gaussian. Okay, we wanted to have something like this as the activation function distribution for each neuron. Okay, so could we actually make it like Gaussian distribution by a transformation? This is the question that we want to answer. And so to make a unit Gaussian distribution, in other words, if we want to have zero mean and unit variance, then we just need to calculate the mean. So the z is actually now is neuron in not the first layer, so we are in layer L. So this neuron has some inputs, and we calculated some of those inputs with these weights and denoted it by zi. So to calculate the mean, we just get the sum over all of these and divided it by the bias of the neuron. Okay, and for the variance, we do the same thing. To do the normalization, we just again remove the mean and divided it by the variance. So in this case, we expect that the output of the neuron, or this z norm, has a distribution like this, or unit Gaussian. But the problem of this method is that maybe if we just normalize in this way, then we could have just this distribution. What if the desired actual distribution is something like this? Okay, or this. Okay, to be able to have some distributions like this, we could parameterize z norm by gamma and beta after the normalization. So first we do the normalization. So now we have a unit Gaussian. Now we scale it by gamma, so we could in fact the network could adjust the variance based on this scale, and we have a beta in here that could shift the distribution, and so we could produce different distributions with gamma and beta parameter. Okay, and the gamma and beta are learnable parameters of the model. Okay, so and also this is interesting that in this case maybe the input of the network is the input of the neuron itself is enough for the network or is suitable for the network to produce output. In that case, with a special setting for gamma and beta, we could recover the input itself. Okay, so this gamma and beta gives us very good and very wide range of choices to have different distributions. Okay. So this is the batch normalization, but when we want to test our network, we don't have any batches to remove the mean from the input layer, right? So let's say this is our network. And now in the training time, for each layer we calculated z minus mu over sigma 2, and actually this mean and variance are the mean and variance of the batch size of the batch of the training data that we sampled. But if we are in the test time, then we have just one input to feed to the network, and we should remove the mean and variance of the training data from that input, but we don't have them. So to be able to do this, one very simple way is to just using moving average mean to remember the mean of the training data. So for each of the batch size, we update the mean by a moving average formula. Okay, so in this case we could store the mean value and the variance value. Okay, so the cool thing about batch normalization is that it is robust to shifting the input distribution, and it could learn different. If we have different distributions, still it could learn the same output. For example, in here, as we could see, we have some cats, but in this case we have some cats with different distribution. So maybe it is just a shift of this distribution, and by using batch normalization layer, we could still have a good performance in the network. So what actually does the batch normalization is that it somehow limits the network, the output of the network, to have some distribution, and so for different inputs it could create the same output, and so it is more robust to noises. Okay, so we could use that when we want to be more robust to different distributions of the input, and also it could speed up the learning process. So you could actually use batch normalization layer to speed up the training process, and also when you use the batch normalization, you could set higher learning rate for your neural network, and because it somehow set or adjust the distribution for the activation functions, it could improve the gradient flow through the network, because your network probably does not saturate in the activation functions. For example, in ReLU, by batch normalization, we probably go back to here, and also in tangent hyperbolic, we'll go there by batch normalization. Okay, and it reduces the strong dependence on initialization, so we could use different initialization but still get good performance. And it acts as a form of regularization because we somehow limit the output distribution of the network, so it could act like the regularization because it reduces the variance of the model. Okay, so this is batch normalization, which is pretty simple thing, but it is really useful to use that in deep learning, especially because of this fact. In deep learning, the main problem maybe is the gradient flow in the network, that we want to have a good gradient flow in the network because we have a deep network and we should be able to train all of the layers to have a good performance. Okay. Now we want to talk about convolutional neural networks or convolutional layers. Okay, so let's start with fully connected layers. So in fully connected layers, when let's say we have a 32 by 32 by 3 image, so this is related to the number of channels of the image. So we have an RGB image, so this image is, when we have 32 by 32 image, then this is the values for R channel and G channel and B channel. So we call it actually a tensor. So we have a 32 by 32 by 3 tensor, which is our image. So in order to use fully connected layers, we should vectorize that image. So we just vectorize this tensor into a vector with just one dimension. To apply the fully connected layer, so let's say we want to have different 10 different outputs. For example, maybe this is the MNIST, and we want to have 10 different outputs. For example, we want to have 0, 1, 2 to 9 as the outputs probability. Okay, so for the activation function, we could use softmax. So we have, if we have 10 neurons in this layer, then the weight vector is 10 by 3072, which is quite a lot. And in fact, the number of parameters in the networks that uses the image as the input in fully connected layers or in dense layers grow very rapidly, and so we are prone to overfitting when we use just fully connected layers or dense layers for the input images. Okay. Okay, so now we know the number of parameters would add up very quickly when we use fully connected layers, and also it could lead to overfitting. So instead of that, we could have a different architecture that we want to talk about it in next slides. So we call this CNN, or convolutional neural networks. So basically we have the input, and these are the neurons of the next layer, and as you could see, each neuron in the layer is corresponded to a local region in the previous layer. Okay, so let's see in here when we have one neuron is corresponded to all of the inputs. So all of the inputs are multiplied by this W to create this one neuron. But in here we have seen different thing. So this neuron is corresponded to just this region of the input image. Okay, so this is the idea. This is in fact one of the ideas of using convolutions. Okay, so the first network in fact which was very successful in some tasks was Alexnet, and the second network was Alexnet, which we have seen in the benchmarks that we talked about deep learning. Okay, so to build convolutional neural networks, we need convolutional layers, we need pooling layers, and fully connected layers. So we already know about fully connected layers or dense layers. So basically they are just connected to, each layer is fully connected to the next neurons. So this is fully connected layer. So we want to talk about these two layers. So in convolutional layer, as I said, the output of neurons are connected to a local regions in the input. So instead of one neuron being responsible for all of the input, each neuron is corresponded to a limited region in the input. And these convolutions have some filters or some parameters that we could learn. Let's see what we mean by this. Okay, so a convolutional filter or convolution is basically, let's say we have a 7x7 input, which could be our input image, and in convolutional layers we have the weights are filters. So we could have 3x3 filters. To get the output, or to so now when we had fully connected layers, to get the output we just applied these weights to the input and then calculated the output. Okay, now our weights are some kernels. We call these kernels or filters. Now we want to know how to calculate the output. Okay, so if this is the input, okay, like this, in this case these are the inputs, so in this case we have a 2D input, and this is the filter, so it is, we could consider that like these weights. To get the output, we just need to sweep this filter over this input. So first we put this filter, let's say this is W1, W11, W12, W13, and this is W33, and this is, let's say this is I11, I12, I13, and so on. Okay, so first we put this filter over here to calculate the resulting output for this pixel. So the output for this pixel that is related to this one in the output map is W11, I11, W12, I12, and to W33, I33. Okay, so this is how we calculate the output for this pixel. In other words, for this pixel. So in other words, we are just doing some blending, or we are doing some kind of weighting for each pixel with consideration of its neighbors. Okay, so instead of having one pixel as the value, we replace that with a linear combination of the local neighbors of its pixel and the pixel itself. Okay, so after created this output pixel, we move this by one, we move this filter, and then create and then calculate the output for this pixel. Okay, so this is the second output, and we do this for all of the outputs. Okay, and as you could see, we cannot put this filter and calculate the output for this pixel, because for this pixel we don't have any pixel in above, so we could not put the kernel or put the filter in here. Okay, because we don't have any pixel value in here. So the output size is less than the input size. So in this case we have 7 by 7 input, and because the filters are 3 by 3, we have 5 by 5 output. Okay. So in the images, if we have a 3 depth or 3 channels image, our filters are 5, let's say our filters are 5 by 5, and then they should have 3 channels to be able to actually put them on this image. So to calculate the output of this filter multiplied or convolved with this input, we just put that on here and just calculated the dot product between this filter and this region, and created the first pixel of output and created the output in here. Okay, so the good thing about this is that it could preserve the spatial structure. Why? Because in the output, again, each output neuron is related to a local region in here. In dense layers, each neuron is related to all of the inputs, so the spatial structure is not preserved. But when we use convolution layer, the spatial structure is preserved. And the convolution actually is meaning that if you don't know the convolution, it's just meaning that we slide this filter over this image. So we first put the filter in here and calculated the output, and then shift this to calculate the output for this pixel, and so on. So we call this convolution, okay, convolution operation. Or in other words, the output is equal to, if we call it f, it is the convolution of f by the input, let's say it is I, okay. Now we have a more clear image in here, okay. So as you could see, now our weight vectors are some filters, and we just put this filter and slide it over all the image to calculate each neuron output, okay. And the great thing about this is that if we wanted to use a dense layer in here, each output neuron should connect it to all of these inputs, and in that case the W we saw that has 3072 parameters, but when we use this filter, the number of parameters is just 75, right? So we have a great decrease in number of parameters when we use convolution, and that is so great about convolutional layers. Okay. And you should note that when we use the filters, the size of the filters are hyperparameters. So you could change the number of filter size. It is in the design of the neural network, but the number of channels in your filter is determined by previous layer. So if you have a 3 channel image, your filter should have 3 channels. So if you want to have 5 by 5 filters, the number of channels of each filter should be 3, okay? Because we want to calculate the dot product, and to have the dot product, we should be able to match these channels to the number of filter channels. So we slide the filter over all of the image and calculated the output. So the output has just now 1 channel, right? Because we calculated the dot product in here. So when we calculate all of these products in here, we just get 1 number or 1 neuron, okay? So the output activation map has just 1 channel if we use 1 filter, okay? So just note that when we have 32 by 32 and we apply 5 by 5 filters, the output result is 28 by 28, or so we have some decrease in the size of the network. What if we apply another 5 by 5 filter? Okay, so if we apply a second filter to this image, now we have the activation function for the first filter. Now we have the second activation function, which is related to the second filter. Okay, and we could apply this for example, for 6 different filters. The output result is 6 activation maps. Okay, we call this activation maps. And if we want to now apply another set of convolutions or convolution filters in here, those convolution filters should have 6 channels, right? For example, if I want to apply 3 by 3 kernels, they should have 3 by 3 by 6 channels to be able to match these channels to the number of filter channels. Okay, so the depth of the output volume equals to the number of filters. So in here, when we apply 6 5 by 5 filters, we have 6 channels as the output of resulting convolutional layer. So now we could apply these convolution layer. So we have convolution layer and ReLU. So after calculating the output neuron, we could apply the ReLU on that to get the activation map. So now in here, as you could see, we have 6 channels, means that we used 6 filters, and in here we have 10 channels, means that we have used 10 5 by 5 by 6 filters. The 6 because we have 6 channels in here, okay, and so on. And as you could see, we have decrease in the widths and heights of the activation maps. For Alexnet, if we visualize the first layer filters, we could see that these are the filters of the Alexnet. And from point of computer vision or image processing, in fact, these filters are extracting some kind of features from the input image. For example, this filter maybe could be related to something like, so we have some values as 1 or some high values in here, and let's say we have 0 or -1s in here, and this filter could extract the edges in the image with this orientation. So we could extract this kind of edges in the image by using this filter, okay? And as you could see, we have different filters to extract different textures and different features from the image, okay? So this is an example of, let's say we have 32 filters, 32 5 by 5 filters, and if we apply that on a part of car, we could see the activation maps in here, okay? So for example, as you could see, this is some kind of blob detection maybe. So the activation function is more sensitive for these regions, okay? So each filter is somehow has different duty to extract different features from the image or decompose the image into different features to make it for the network more easy to get the decision, okay? And so this is the convolution that we talk about. It's just the multiplication, the element-wise multiplication of those signals, in fact, and then slide over the filters and do the same thing, okay? So for example, when we want to detect whether an input image is car or not, first we apply the first layer filters, and after that we apply the activation functions. So as you could see, now we have these edges, different edges, or different, we extracted different features from this image, and again we apply the same thing in here. After that, we should vectorize the output and create a fully connected layer to create the classifier. So at the last layer for classification, we should have a fully connected layer, okay? And we could see that we could get by applying the softmax activation function, we could get the probability for car or for the input image. Okay. So now we know how to calculate the output. So you have seen that we just, for calculating the output, we slide over the filter 1 pixel by 1 pixel to calculate the output. But sometimes maybe your input resolution is so much. So maybe you want to have smaller output or activation maps. In this case, you could use strides with more than 1 pixel to calculate the output. So this stride 2 means that for this pixel, we calculate the dot product between this filter and this part of image. After that, instead of moving this filter by 1 pixel, we move that by 2 pixel to apply this on here, okay, and so on. So as you could see now, we the filter jumps 2 pixels, okay, to calculate the next output. And this means that we have the 2 stride. Okay, so at the end we have 3 by 3 output when we use a stride 2. But if we use a stride 1 with 3 by 3 filters and 7 by 7 input, we had 5 by 5 output. Okay, and we could apply the same rule to get the output size when we have n by n input and the filters is f by f. So the output size is n minus f over stride plus 1. Okay, so when we use, and this plus 1 is actually so maybe it is better to write it is in this way. Okay, so for example, when we use the stride 1 and the number of input is, the input is 7 by 7 and we have 3 by 3 filters, then we have 7 minus 4 over 1 plus 1 as the input. This is 3. 7 minus 3 over 1 plus 1 as the output, which is 5. And we could do that so on. So as you could see, for some numbers we couldn't use this stride. For example, with 7 by 7 input and 3 by 3 filters, we couldn't use the stride 3 because the output size will not be an integer. Okay. Sometimes maybe we use the zero padding or some kind of padding to get the bigger activation functions. Okay, so for example, before the convolution, if we have 7 by 7 input and we zero pad the borders, so now we could calculate the output also for this pixel. Okay, so the output size in this case will be 7 by 7, and if we use zero padding or other kind of paddings, we could have the same output size as the input size. Okay, so this is sometimes useful, and the output size in general, if we use padding, is m plus 2p minus f over stride plus 1. Okay. Okay. So also we could have the 1D example of convolutions. So convolutions are not necessarily 2D filters. We could have 1D filters and 1D one-dimensional inputs. Okay, so in fact, in convolution layers, when we use convolution layers, we are using the local connectivity and sharing between the weights. So to get the output, if this is the input, we could apply the same rules as the 2D convolutions in here. Okay, we will see that more in the next sessions. Okay, so in this case, when we use this kind of architecture for the network, you will see that your spatial size activation functions, the spatial size of activation functions are reducing so fast, and this could prevent us to create deep neural networks, and it doesn't work well sometimes. So to preserve this, we could use the padding, for example 0 padding, to get the same spatial size in here. So by introducing 0 padding, we could get the 32 by 32 over different layers. Okay, so in these cases we use 0 padding. Okay, so in here we are seeing the common patterns for number of filters. The number of filters are typically 32, 64, 128, and so on. They are the powers of 2 commonly. And for the filter size, we could use 3, 5, or 1 as the filter size. And what does it mean to use 1 by 1 convolutions? So in that case, our convolutions are just 1 pixel. So we just calculate 1 pixel, but the number of channels are equal to the number of channels of previous layer. So we are some kind of computing the linear combination between these channels to get the output. And this is cool because maybe we could interpret that sometimes it could act like PCA. So for example, in here you have 64 channels and you reduce it to 32 channels. And we will see that this is really useful when we want to create large networks to reduce the number of parameters. Okay. So now we know all of the things about the convolution layer. Okay. So we have 2 things in convolutional layers as their characteristic. So we have local connectivity. It means that each neuron the output is related to a local region in input. We call that receptive field. We call here receptive field. And because the features, so in a large input, typically the features that we are extracting in here, and they are useful, so they are probably also useful in there. Okay, so we are using the same filter over all of these image. Okay, so this is the reason, because we think that the features that are useful in here they are also useful in all over the place of the image. So we are using the same parameters over all of the image. So we have parameter sharing, okay, for the convolutional layers. Okay. So what are the pooling layers? So sometimes our inputs are really maybe large, and we want to have some kind of downsampling to make them smaller. In this case, we could use pooling layers to reduce the number of spatial size dimensions for the activation functions, for the activation maps. Okay. One of the popular methods for pooling is max pooling. So it means that when, for example, when we use 2x2 max pooling, it means that with stride 2, it means that we divide the input to 4 different regions, as you could see in here. Then instead of having all of these pixels, we just pick the maximum value, which is 6 in here, 8 in here, and 3 and 4 in here. Okay, so this is the max pooling layer, which is pretty easy to understand. So it could reduce the spatial size of representation, and so it could control the overfitting, because in the last layer, when we want to vectorize this and create a fully connected layer, we should have a reasonable size, a reasonable spatial size for this activation function. Okay, so yep, that's it for the convolutional layers and convolutional neural networks. This is a common pattern in convolutional neural networks. We have convolutions, we have some activation functions and pooling layers, and to the fully connected layer to get the output. Okay, I hope you enjoy from this session, and see you in the next session. Bye.